thank you all for being here. It's my great pleasure now to welcome you for our second DSS. So this is the CCMA Distinguished Lecture Series hosted by the Department of Civil Environmental Engineering. So I'm Lydia Boriba. I'm the faculty organizer of the series, and the goal of this series is really to bring state-of-the-art researchers and distinguished speakers from around the world with a certain focus in fluid mechanics and mechanics, but then also the broader areas that pertain to the civil environmental engineering department, the MIT community, and the broader Boston area. So this term, I just want to give a little bit of advertisement for what's coming before then passing it to my co-organizer to introduce our speaker of the day. So this term we're going to have a total of 5 speakers, a couple in fluid mechanics, some in basically structure and sensing, others in transportation and modeling. And so you can now check all of these updates in a short version of the website name, which is dss.mit.edu. And so you can just go there and see all the updates. And another piece of advertisement I want to give is that we record these lectures. And so even if you miss them, and there is some that are of interest, you can go on the site. And except for a few speakers, they're all generously agreed to have their talks online. So you can actually see the talks and use them also for lectures. Today, we are basically honored to welcome Professor Arif Masud, and I will leave his detailed and full introduction to my co-organizer, Professor Oral Buyukos-Turk. I never actually pronounced your last name.
my first name. Thank you, Lydia. Thank you so much. Thank you very much. Actually, Lydia and Carol, Lydia organized it, and they did a fantastic job in this organization, really. Thank you for that. And it's a great pleasure to introduce our distinguished speaker today, Professor Arif Masud. He has a very long bio, as you might imagine, but I tried to cut it as much as I could. Dr. Masud is a professor and the head of mechanics and structures in the Department of Civil and Environmental Engineering, and also professor of the Department of Aerospace Engineering at the University of Illinois in Urbana-Champaign. He holds the title of Robert H. Dodds Faculty Scholar of the CEE department there. Dr. Masud received his PhD in computational mechanics from Stanford University in 1993. He worked with actually Professor Tom Hughes there, who's a computational mechanics expert, well known. Professor Masud has made fundamental and pioneering contributions to the development of multiscale methods for fluid and solid mechanics, turbulence models, non-Newtonian fluids, and porous media flows. He has an extensive publication record. He co-authored the book entitled Finite Element Method, 1970s and Beyond. He is the past chair of the Fluid Mechanics Committee of ASME and the Computational Mechanics Committee of ASCE. Has served as associate editor of the ASCE Journal of Engineering Mechanics, ASME Journal of Applied Mechanics, and ASCE Journal of Nanomechanics and Micromechanics. So you covered a broad scope of mechanics there. Dr. Masud holds a number of fellow honors that I cannot finish reading, but the ones that I want to mention is the AIAA, ASME, and EMI ASCE fellow. So I think with that, I would like to welcome him for his lecture, and thank you very much for accepting our invitation.
Thank you, Ral. I'd like to take this opportunity to thank Professor Oral Buyukos-Turk and Lydia for inviting me here and your Department of Civil Engineering to this distinguished lecture series. Today, what I'm going to talk about is a new class of variational multiscale methods, and I'll describe it in the context of developing residual-based turbulence models for large eddy simulation, and then application of multiscale methods to non-Newtonian biofluid dynamics. This is a CCMA distinguished lecture series, And so I've brought a whole bunch of problems here, problem classes. It reminds me of the distinguished career and the seminal contributions from Professor May in the area of hydrology and coastal and wave action phenomena in ocean engineering. So here is a problem of turbulence, free surface flows. This is a free surface breaking against structures. And these are example problems from hydrology. We could be interested in modeling turbulence around airfoils or hydrofoils, or modeling the phenomena of energy transfer from the flow into the structure for energy harvesting. And then there is another class of problems, which is confined flows, blood tissue interaction or blood artery interaction. And in here, the constitutive model for the fluid is more involved than of air and, of course, water. It's viscoelastic, shear rate dependent. So these are, an elastic artery by itself may be undergoing viscoelastic deformations. And since it's a tissue, and tissue grows, adapts, reconfigures itself to mechanical and stimuli, as well as to chemical stimuli. So modeling of tissue is not just an elastic material, it has more features to it. So if you want to address these classes of problems, then the question arises, what should be the underpinnings of the numerical methods that can address this wide array of technical issues that arise in here? And in this talk, I'll try to highlight the commonality of the issues between these problems as we develop the method. And so the focus of this talk is going to be on method development. The objective of research in my group is develop new numerical methods that have enhanced stability and accuracy properties, and emphasis is on mathematical constructs that have wider applicability both to fluids and to solids. And the idea is that if we can develop unified mathematical frameworks that can be applied to a wider class of problems, then we have a better chance in developing robust algorithms when we apply it to problems of multi-physics problems from engineering and science. If we take a moment and look at the classes of problems that are really posing challenge to the state of numerical methods or status of numerical methods today, they invariably involve multiple interacting physical phenomena, interacting in a nonlinear fashion, involving scale effects, and having strong or weak discontinuities. In other words, numerical methods for mathematically non-smooth multi-field problems is the name of the game. If we look at turbulent flows interacting with structures, blood tissue interaction, at newly emerging field of additive manufacturing, these are all problem classes of multi-field problems. And in all of these problems, flow mechanics, flow rheology, fluid structure interaction appear in very unique ways. So here is an outline of what I'm going to discuss. I'll present variational foundations of multiscale methods and talk about the enhanced stability features. These methods that I'm going to present here come equipped with error estimation feature, which I will highlight. We will use these ideas to develop closure models for large eddy simulation, and these are residual-based closure models. Once we have the variational formulations in hand, we will embed in it viscoelastic constitutive models that represent biofluids, and I will show how fine-scale modeling concepts can be used to impose the constraints on the elastic stretch of the viscous stress tensor. I'll couple it with the blood artery model. The artery itself can grow. We'll discuss briefly that particular issue, and I'll talk about the coupled solution algorithm and inherent stability of the algorithm because of the stability of the formulations, and finally round off my talk with some concluding remarks. So this slide here looks at a model problem, and let's look at the variational foundations of the multiscale method. L is the differential operator. In the present context where we are talking about Navier-Stokes equations, this is the operators of the Navier-Stokes equations. U is the vector, and in the present context, it will be velocity and pressure field, and then we have the source term. L is going to be nonlinear in this case. And this is the generic model problem, and if we could be talking about elasticity, then nonlinear elasticity, L would be the operators of elasticity coming in. So we take this weak, strong form, we multiply by a weighting function, and integrating over the domain, it gives us the Glerkin form. And once we have the Glerkin form, we can make the mesh, and let's say we solve a problem, and let's say this is the solution that we want. It has coarse scales or a mean solution and fluctuations. With a decent mesh, we are able to capture the mean solution, and the fluctuations or fine scale effects are filtered out. Mesh behaves like a filter, and anything that is of the order of characteristic scale of the mesh which is the parameter h, is filtered out. And within the context of Galerkin method, the way to capture these features is to refine the mesh. And if you walk along this line of thought, it's very limited in its scope, because these days computational mechanics is being called in to give us solution to large problems, multi-field problems, where the phenomena of instability occurs at a very, very small point. Turbulence is one example. Crack propagation in solid mechanics is another example. So the question is, rather than trying to capture these features with the force of the mesh, is it possible that we can develop a method where these features and the effects of these features can be accounted for in the features that are computed? In other words, can we develop numerical methods that have the ability to capture the fine-scale phenomena? And with that point of view, we will proceed. So we have total solution, a part that we can capture, and a part that is filtered out. What is filtered out is the error. Error is also a solution to the governing equation. So we take this additive decomposed form of the solution and plug it in the weak form. Whether this operator is linear or nonlinear, this weighting function is always linear, so we can split it analogously into coarse and fine scale and substitute it here. So we have a multi-scale weak form where both the coarse and fine scales are here, as well as in the weighting function slot. This becomes the point of departure from the standard classical Galerkin methods. Now, the key idea here is that we use the linearity of the weighting function slot in here to decouple this problem into a problem that is coarse scale problem, which is weighted by the coarse scale weighting function, and a fine scale problem, which is weighted by the fine scale weighting function. If you look at it, it still has both coarse and fine scales fully embedding in there. And now we are going to focus our attention to fine scale problem. This is going to be like a mathematical zoom, and we will take a look at this. An objective is it possible that we can extract a model for fine scales through this problem? And then if so, we can then embed it into the coarse scale problem to represent this effect. And that is going to be the key point in here. So if you look at fine scale problem, U bar is the coarse scales, and suppose for a second that coarse scales are given to us. And in a nonlinear setting, we know we go from step n to n plus 1. At step n, we get the converged solution. That converged solution is known to us. That is a coarse scale. And we go to the next step. We are trying to find the missing scales. So we can take U bar to the right-hand side. And if we take it to the right-hand side, we immediately realize that fine scale problem is, in fact, driven by the residual of the Euler-Lagrange equations of the coarse scales. So it means fine scales are consistently derived based on the residual. What is not accounted for by the coarse problem is what the fine scale is going to be. So we can extract the expression, analytical expression for fine scale. And at this point, idea would be try to find either an analytical expression. If not, then numerically find the coefficients and reconstruct the field. So once we have fine scales, we can then embed into the coarse scale problem, and this is what we are going to get. I've color-coded them. The terms in the black are the standard Galerkin terms, so Galerkin is fully preserved. These terms have appeared, and what they are doing is they have appeared because of the assumption of existence of fine scales, which are not captured by the coarse mesh, and these terms are, in fact, modeling the effects of fine scales. And so if you look at this expression, the prime terms, fine scales, have disappeared. Rather, their effects are being modeled by these two terms that have appeared. Once we capture this solution, so this is the modified stabilized form. Once we get the solution, we can go back and we can evaluate the residual and see how good our estimation was. So this is the general framework, and I will show how to apply it to Navier-Stokes equations. These are incompressible Navier-Stokes equations, momentum balance equation, continuity equation, velocity and traction boundary conditions and initial conditions. Here V is the velocity, P is the pressure, F is the body force. We developed the standard Galerkin form by defining the appropriate spaces of functions for the velocity and pressure, multiplying, integrating, and this is the standard Galerkin form. Standard Galerkin form suffers from two drawbacks in the context of incompressible flows. Number one, not arbitrary combinations of velocity, pressure, interpolations, functions work. And what works in 2D may or may not work in 3D. And therefore, there have been techniques that have been developed called stabilized methods. And the other thing is, this convective term needs special attention, and because it can produce layers, so in order to address this issue, stabilized techniques have been developed. SUPG, streamline, upwind, Petrov, Galerkin, and Galerkin least square methods have been developed. These methods have stabilization parameters that are based on design that is achieved through nodal exactness in 1D. Nodal exactness can be obtained for linear problems in 1D, but not even in 2D for linear problems. So that has been the issue in that context. What I will show is a stabilized formulation that we will derive here based on the framework that I just presented on the last slide. So we proceed with taking the multiscale, assuming this multiscale decomposition of the velocity field into coarse and fine. Weighting function is split between coarse and fine. We substitute it in the weak form. Using the linearity of the weak form, we split it into coarse and fine scale systems. This is the momentum balance of the coarse scale system, momentum balance of the fine scale system. As I mentioned, the idea is to solve the fine scale problem and extract an expression for V prime that can then be substituted in these two. Now, this fine scale problem by itself is as involved as the original problem. So in order to resolve that, we will need to make some modeling assumptions. And we will come back to evaluate those modeling assumptions through the error estimation procedure. So this is the momentum balance of the fine scales. We assume that the fine scales are a piecewise constant in time. We are taking mean value. We will relax this later on as we move on. And we say fine scales are a combination of bubble functions. Bubble functions are functions which are non-zero within the element. They become zero on the element boundaries. Again, this is not a necessity, but it helps us extract the analytical expressions for fine scales and be able to take a look at them in a more precise form, and also implement these strategies in parallel computing, because this is element level calculation and very easily amenable for parallel computing. So with this, we can expand the fine scale. So I take this fine scale equation, we linearize it, take all the bar terms to the right-hand side, write in a residual form, substitute V prime and W prime in terms of coefficients, expand it out, get the coefficient for beta, and then multiply by bubble function to reconstruct V prime. That is summarized in here. This can be analytically derived, and we have shown that in our papers. So fine scales are proportional to the residual of the Euler-Lagrange, and whatever we see here is what we call stabilization tensor. So stabilization tensor is not designed. It is mathematically derived based on Navier-Stokes equations, and you can see the operators of Navier-Stokes equations are acting on the fine fields which are substituted or which are represented through these bubble functions. So this can be explicitly derived. Now we can substitute it in the coarse scale problem, and when we do that, we have this formulation. Again, I have color-coded it. Black terms are the Glerkin terms that I showed you in the previous slide. It's fully preserved. All of those terms are there. The term in the blue has appeared because of the assumption of existence of fine scales that were going to be lost in the coarse mesh calculations, and these are proportional to the residual of Euler-Lagrange equations. Method is inherently consistent. It accommodates exact solution. Now we can contrast it or compare it with the standard or the classical stabilized methods, state-of-the-art methods, SUPG and GLS, streamline, Upwind, Petrov, Glerkin method. If we drop this term, the second order term, what we get is SUPG. And if we change the sign of the second order term and add the inertial counterpart in the weighting function slot, we get GLS. So SUPG and GLS are subclasses of this more advanced class of methods, and we have mathematical proofs for showing the stability of the method. I will show you the stability of these methods through some numerical examples. So whenever we design a new method, the first question is it consistent? Is it stable? If it's consistent, stable, you can prove convergence. So in order to do that, we look for, number one, do we have a problem for which an analytical solution exists? If not, we compare it with experimental data. If not, we compare it with other numerical theories. In this particular case, we are going to look at the solution, the exact velocity field and pressure field. We substitute it in the governing equation that gives rise to a body force, run the problem with that body force, recover the velocity and pressure field, and look at the rate of convergence. And I've plotted it here. Linear tetrahedra with equal order velocity and pressure fields. Now, finite element theory states that rate of convergence in the L2 norm for linear elements is 2, and H1 semi-norm is 1. And we have plotted the rate of convergence for L2 norm of the velocity, it is 2, and H1 of pressure is 1. Likewise, for hexahedral elements, 8-node brick elements, we are getting a rate of convergence 2 and 1. And this is a log-log plot. So this is a numerical proof of the consistency and convergence properties of the method. The next example problem, let's take a look at a more engineering problem where a flow is coming onto a structure. circular cylinder, which is attached with a spring. This cylinder at Reynolds number 100 gives rise to vortices. There are vortices formed, and the period of shedding is 5.7. So we have adjusted the mass stiffness of the system such that its natural frequency is also 5.7. This is a strongly coupled flow structure system. So we are going to look at what does the fluid-solid coupling, the nonlinear fluid-solid coupling, does to this particular problem. The governing equations for the mass is shown here, and I'll show you the numerical results. So flow comes on, symmetric pairs, breaks into eddies, gives rise to translating force. This is resisted by the cylinder, by the spring that is attached to the cylinder. We plot the displacement time history, and from there we can find the period of shedding. From there we can find Stru-Hall number, which is predicted as there are experiments done, and these are the values predicted in there. And the maximum amplitude, that is also a measure of the quality of solution or the degree of decay or any extra viscosity in the system. Now, this is a strongly coupled system, flow structure system, and a simple idea would say, well, its period of shedding is same as that of the natural resonant frequency. The system is coupled, it is in resonance. However, fluid structure interaction, nonlinear fluid structure interaction makes it, so this is a phase plot, lift coefficient as a function of displacement of cylinder, 4 or 5 periods plotted in here once the flow is fully developed. And not only it's stable, it's also periodic. So flow structure interaction acts in very unique ways for nonlinear fluid structure interaction problems. And when we are solving these problems, that has to be fully accounted for. I talked about the error estimation feature. This is one snapshot that I've taken out of that simulation. So at one time, 162, this is the velocity field. Once we have the velocity field, we can now go back to our system and we say, total solution was solution that was coarse scale that we were going to capture, and a scale that was filtered out, we modeled it. So now what we have got is a solution where the fine scales are modeled because of the additional terms that we have gotten, but still, we are doing numerical calculations. We have a mesh in there. So any difference between our computed solution and the exact solution is the error. This error has two parts. It has a local error and a global error. Local error is error over the element, and that relates to how good our assumption was that fine scales could be represented with a bubble function. How good that bubble function was. Was it good enough to exactly represent the fine scale features or not? And that can be extracted by going to this expression, which I showed you in the previous slide, plugging the U bar and P in, V bar and P in there, and what comes out is the local error of the element. The cost of computing this local error is just like in solid mechanics when you get the displacement, you go to the element level and you calculate the stresses at the integration points. The cost of computation of this local error is as simple as that. So this is the solution. Add one of the snapshots. For this snapshot, we can analyze it. And here is the spread of the local error. Now the question is global error or pollution error. Global error or pollution error is there not only in fluids, it also takes place in solids. In case of fluids, think of a cylinder, flow coming onto it, and there's another cylinder behind it. The first cylinder produces vortices that get convected, but in between the two meshes, if the mesh, two cylinders, the mesh is not refined enough, you'll lose some resolution there. And that resolution cannot be recovered when these vortices get onto the next cylinder and the mesh is fine, pollution error. Same principle happens in solid mechanics. If you have a cantilever beam subject to an edge condition and you have constrained in here, and your mesh at the root section was crude mesh. And let's say you're using 4-node elements and they respond in shear, bending dominated response. If you just keep on refining under the shear, where you applied the shear, that is not going to give you the exact solution. This parasitic shear is always going to sit in there. So this idea of global pollution error is there both in fluids and solids. So for that, we can go to the variational equations. This was our total solution. What we captured, and fine scales had a global error and local error we just computed. So substitute these in the variational equation. When you substitute it in the variational equation, UH and PH, which was the last converged solution, takes care of the source terms. So source terms are taken out. Then we have these two terms. EL is computed. So terms where EL is appearing go to the right-hand side, and what is left in the left-hand side is your global solution. So one solve with the last factorized stiffness matrix with the new right-hand side made based on the local error gives you the global distribution. And here's the global distribution of the error. And we have applied it for different problems and looked at their capability of rate of convergence. In the context of fluid mechanics, what I want to highlight here is that whenever we are working with, let's say, experimentalists, and we do a numerical calculation, and our numerical simulations are not exactly what we see in the experiments, the first thing that comes to mind is that maybe the mesh is not refined enough. Let's make a mesh and run the problem again. Maybe delta t is not fine enough. Run it again. But if you are able to get this information and you look at this local error and you look in the boundary layer region, and this was the boundary layer region that was producing the stresses that provided the force for the motion of this thing. And in here, if you see that the residual is error is 10 to the power -5 or -6. And now if your solution is different from experiments, then maybe something else is wrong. So it can help you reduce the number of unnecessary calculations, or it gives you a degree of confidence in your calculations that if you're going to make a decision based on these calculations, how much confidence you should have in terms of these calculations. It's not only giving you physics, it's also giving you the distribution of error in that calculation. So with these things in hand and scale effects in hand, let's take a look at another tough problem. In this problem, there's a flow, this is called dam break problem. It hits the structure, large amplitude motion. It cannot be done with moving mesh type techniques. So we have embedded in it a level set based idea, level set techniques, but level sets by themselves are inherently unstable, so they have to rely, so your underlying mechanism for solving the Navier-Stokes equation has to be very stable so that the resulting system is also giving you a stable response. This is like breaking waves hitting against the structure. So because of the inherent stability of the Navier-Stokes equations, the model that I showed you, we can embed that. And I'm showing you the pressure pulse at a point in the middle and a point at the top. Wave takes some time to hit the structure. There's a spike, and then it relaxes or eases off as the water column height reduces. And here's comparison with the experimental data. So again, stability of the method becomes very important for solving some real tough problems. And I think this class of problems is going to be very significant if global warming becomes an issue. It becomes a real issue, then we will see civil engineering departments across the country. A major effort will be defend the coastline from the salt water that is coming on shore. So that could be a very important problem in time to come, provided. So it can give rise to what is called smart coastlines. That's an issue that I foresee coming in the future. Now that we have talked about scale issues, let's take a look at large eddy simulation. Eddies or turbulence is all about scales. It's a story of scales. And if you look at the wave axis, wave number axis, given any mesh, it has a resolution capacity. So any scales that are small, that are larger than, yes, we will be able to resolve, but then there's an infinite number that is lost thereafter. The current techniques for turbulence modeling introduce a model. And that model is based on inducing, whether it's Mogrinsky type model or dynamic model, it's going to introduce some viscosity in the system to account for the energy decay that is going to take place in the fine scales. So our line of thought here again is going to be, can we use the line of thought that I presented before? And based on that, can we derive the mathematical equations that will do that? And are those mathematical equations terms variously consistent? These are two major things that I will try to address here. So we don't want to add a model in any place. We want to derive this model, and that is the contribution that we have had shown in these papers. So the idea is, again, a three-step process. Based on the scales for coarse and scale for fine, we need to split the functional spaces of coarse and fine scales so that there is no overlap. That is a requirement of the method. Once we define that, we will have a coarse scale and a fine scale problem. And idea will be take the fine scale problem. This fine scale problem is going to be as hard as the coarse scale problem. So you need to make some modeling assumptions. Question is, are those modeling assumptions reasonable? I'll address that. We will extract an expression from there, and we will use this bubble functions approach that I just mentioned. And now question will be, how can we use it for a more elaborate system? And if we can do that, then we can mathematically substitute it, and that will be the closed form expression for large eddy simulation. And I'll present that to you. So now we move forward. Our velocity field is coarse and fine. Previously, we did not split the pressure field into coarse and fine, but now we are trying to develop a model which is going to address a cascade of scales. We need to give it more flexibility. We need to take the assumptions away. So previously, I said velocity and fine scale velocity is piecewise constant. Now I will not make that assumption. Previously, I said there are no fine scale pressure fields. Now I will not make. So we are now trying to make the fine scale model more relaxed so it can give us a better representation of fine scale model. So we substitute that in our momentum balance and continuity equation, and it gives us a coarse scale system and a fine scale system. So structure of the variational framework is still the same. But our fine scale model problem has a momentum balance for fine scales and a continuity for fine scales. So this is in an infinite dimensional space. Actually, between the two, this is a harder problem. So now question is how to make it manageable, so it's tractable, so that we can extract the expression for V prime and P prime. So if I write the fine scale problem in here, it's a mixed field problem. Mixed field problems are again subject to the conditions of combination of interpolation functions, even if you want to solve it numerically. So what we do is we then look at the scales, and we said, this is coarse scale, here is a fine scale, and maybe for the case of turbulence, which is a cascade of scales, one scale separation may not be enough. We can hierarchically apply this idea. So we have a scale, further split of the subgrid scales into an intermediate scale and fine scale velocity field. And this fine scale velocity field is V2. So fine scales are split into 1 and 2. And now what we have done is we have now made a more elaborate system for us to be able to extract the expressions for V prime and P prime, which are going to be our model. And that is what I'll show next. So this is the schematics. We are doing a top-down scale split, velocity and pressure field, into coarse scales that you can resolve on the mesh, and fine scales which are not resolved. And these non-resolvable scales, we want to extract expressions for V prime and P prime. And we realize that when we are going for turbulence, not only V and P should be time dependent, we need a further split of the fine scales, this hierarchy split. And in this case, we are splitting it into the velocity field alone. This model, two hierarchical splits, is sufficient to give the turbulence model. We will now, so the model development is backwards. This is a split. We will solve the fine scale level 2 problem, get an analytical expression for V2, which we'll plug in here. This will give it as an unconstrained intermediate level problem where all the assumptions have been relegated to level 2, and solution of this problem will be embedded in coarse scale. So that is the model build up backwards. So coarse scales have fine scales, so this is going to be, we have done top-down decomposition of scales and bottom-up building of the models. It's along similar lines that I previously discussed. So let's go to level 2 problem. And here we are using bubble functions. And as I've said, that between coarse and fine scales, your spaces should be linearly independent. And between the fine scales also, your functions should be independent so that you are not double counting the energy. So we can use, for example, in here, 4th order bubble functions and expand weighting function and solution, fine scale velocity and weighting function into the equation, solve for it as I was talking about, and in the wash what we'll get is what is in the red box. The fine scale velocity that comes out is a function of the residual of the momentum balance equations as well as the residual. So this is the residual of Euler-Lagrange equations at level 1. So it means very, very fine scales are acting on the solution, on the part of the solution which was not resolved by any of the other two preceding scales, preceding levels. And in this particular formulation, if you see the fine scale viscosity surviving, so very fine scales also have viscosity, and the operators are Navier-Stokes operators, nothing else. The structure of tau appears in these calculations as similar to what I had shown you before, and we will embed this into level 1. So when we go and embed in level 1, we realize that since the velocity and pressure are both time dependent, we don't have an algebraic system, we have an ODE. Now, solving this at that level will need a little bit more mathematical manipulation from us. We have used generalized alpha method. You can use a method of your choice, absolutely free. So expand, integrate in terms of generalized alpha method, which we have done, and integrate in time, we get this expression for V1 and P1. And it is a function of residual of momentum balance equation and continuity equations. This is the main thing in here. So fine models are acting on what was not resolved at the preceding. And it has information from its lower level models. These are some time-dependent terms, and at the integration point, and we have shown some calculations in which even if you drop it, it doesn't affect your calculation of your solution. So the model is this particular term. These terms you can ignore, as I will show in some of the calculations. If you want to keep these history terms, nevertheless, they don't hurt you. And these are the history terms. If you ignore them, it gives you an approximation of this model where this term has been dropped out. It will tremendously reduce the cost of computation. So when we develop the model, if we can use some not intuitive ideas based on doing numerical calculations and reduce the cost, that would be an attractive feature of the method. So embedding it in the closure model, into the coarse scale, this is what we get. The terms in the black are, again, Galerkin terms. They have not been touched. I will walk you through the other terms. I had shown you in the previous development the stabilized method in which these two terms were sitting there. All the other terms were not there. These terms have arisen because of now a more relaxed method. Our velocity is time-dependent, and our pressure is time-dependent. And what we get in here is time-dependent fluctuations of velocity and pressure. And I'll make analogy with the current turbulence models. In turbulence literature, these terms in the red are the cross terms, and these green terms are called Reynolds stress terms. But in this particular model, they have been derived. So there are two things in this model. Number one, all these derived terms are variationally consistent because they have been derived based on the residual. Number two, you can think of it as doing DNS on coarse meshes. DNS, direct numerical simulation, is Navier-Stokes equations without any model. In these calculations, the fine scale model is derived off of Navier-Stokes operators acting on the fine scales, which are function of the residuals. So all of these terms are residual Navier-Stokes based terms. Now I will show you some numerical results with this particular model. The first test case, as I said, whenever you develop a method or propose a method, there are certain benchmark test problems that you have to solve. The first one in case of turbulences is a decaying energy from larger modes to smaller modes at the Kolmogorov rates. So we embed energy, we put energy in the larger modes, and we try to look at the decay. This is 2-point third-order correlation function. The blue line is DNS results on 256 cubed mesh. And I'm going to show you results for 32 cubed and 64 cubed in here. And in this range, we are getting this asymptotic rate of 4/5 law, Kolmogorov law. This is Fourier transform of autocorrelation function. And again, for 32 cubed mesh and 64 cubed mesh, we are getting asymptotic -5 third law. So larger eddies are breaking into smaller eddies or decaying the energy at the predicted rates. The next case is turbulent channel flow. This is a statistically stationary problem, and we look at in the wall normal direction. So we have applied no slip conditions on the blue surfaces and periodic boundary conditions on the other surfaces. This is driven with a body force and two test cases of Reynolds stress of 395. This is stress at the boundary layer, real number in the boundary layer, and 590. And for that, DNS results are available. So now we are going to compare it with the DNS numerical results. This is streamlines and volume rendering of the velocity field streamlines, and we have added some particles in the flow. These are massless particles, and their distribution is showing the general structure of the boundary layer. But we can go in, and turbulence is a chaotic phenomena, but statistics of turbulence can be compared. And so we look at the mean streamline velocity and RMS of the velocity fluctuations, mean streamline velocity in the wall normal direction. This blue line is DNS results on 256 cubed. And I'm showing you results for mesh, which is composed of 32 cubed nodal points. And for different elements, 8-node hexahedral elements, and 4 and 10-node tetrahedral elements, the number of nodes are same. The element types are different. So linear and quadratic elements, and they are uniformly showing this. So 4-node tetrahedra, start working for this problem because the very fine scales have the viscosity of the system embedded in it. These are the wall normal fluctuations, wall normal direction. This is along the flow, this is wall normal direction, and here is the span-wise direction. Now, between this one and the next slide, we are going to refine the mesh. And if you look at the screen, this is closer to the DNS results. If you have a variationally consistent method and the DNS results are Navier-Stokes results, then this model should converge to Navier-Stokes. And as we refine the mesh, we see this feature in there. We have also solved for a higher Reynolds number. This is 64 cubed mesh, whereas the reference mesh is much refined. And again, hexahedral elements, 4-node and 10-node tetrahedra. 4-node tetrahedra, which are very attractive from the point of view of industrial applications and fail miserably many times in case of turbulent flows, they become competitive via this framework because you are embedding the physics which is otherwise lost, and you're embedding the physics proportional to the residual, not extra, nothing less. The next important problem is that of cylinder, flow around a cylinder. This is an important problem from civil engineering perspective, but this is also an important problem because we look at transition from laminar to turbulent flow. The no-slip conditions are imposed, and it has 2.4 million nodes, 10 million degrees of freedom. Here is the schematics. So as these layers detach, and they burst into periodic vortices in here. And we have added particles in it, and these particles are color-coded, and they change color, so they age, so they're to show the chaotic nature of the flow. We'll be looking at pressure on the surface of the cylinder and the analysis of this flow in the wake of the cylinder. This is the mean pressure on the surface of the cylinder, statistically mean pressure, and we are comparing it with the experimental results, finer difference results from Pervez Moin's group at Stanford, and our method with finer mesh, and we also did results for the coarser mesh. And the coarser mesh, in the coarser mesh case, when we analyze the system, we see that the fine scale problem is working hard for us. But as far as the physics is concerned, it's able to reproduce the physics. So while in the coarse scale, finer mesh, fine scale problem takes 2 iterations. In this particular case, it was taking 3 iterations, 1 iteration more per step. But still, we are able to recover. So if you look at, so where is the saving? These calculations, local calculations for calculating the fine scales are element-based. And these days, the processing nodes of the computers, supercomputers, they have local memory. So we have increased the local calculations, reduced the size of the mesh to reduce the communication cost. And in reducing the communication cost, you gain tremendously in terms of the overall efficiency of the method. This is the mean streamwise velocity behind the cylinder where the flow is extremely turbulent. Statistics is comparable, and here are the results with the experimental data. This is the streamwise velocity and mean fluctuation at x equal to 6, 7, and 10. Again, good correlation with the experimental results. Next problem is airfoil 7003. This problem was motivated, Jaime, by one of your papers that I was talking about. In this case, we have 2 meshes, 1.2 million, 1.6 million nodes, 2 different delta T. Laminar flow breaks into transition, reattaches. In between is a bubble, and we'll take a look at bubble. We have taken the flow features out. We have added the particles, and you can see these particles are getting sucked in. They're color-coded, so they're telling you that they have been staying there long enough, and they show the general pictorial representation of the bubble. And this is an important problem. If the back suction velocity is high, then this flow will become unstable instantly. In this case, the back section is slow enough, so it reattaches in here, and that statistics we can look at here. So this experimental results for separation, reattachment, and length. AIAA, finite difference method. Uranga is MIT, Jaime Prairies group in here. And for all these cases, we have 2 different meshes, 2 different time steps for tetrahedral elements, and we are getting comparable length of the bubble. This is the distribution of pressure on the top surface. At the bottom, the flow was laminar. At the top, it becomes turbulent, separates, and reattaches. And here is the results for that. And again, the lift CF coefficient, friction coefficient. The next simulation is same airfoil, and we are going to give it a periodic motion. So it is now turbulence in an ale frame. Here's the flow that comes onto the structure. This small vortex that appears, it grows, becomes non-symmetric in third dimension, and breaks, so breaks into turbulence. So larger vortices breaking into smaller, we can easily do that. Question is, can we predict the appearance of small vortex and that growing? So small scales feeding into large, large into small. And as I told you, as I showed about the structure of the framework, that small scales are driven by the residual of coarse scales, and we have embedded the fine scales back into coarse. This is a representation of the numerics related to that. Again, lift coefficient and drag coefficient over the period of oscillation, and at 2 different points, we have compared the results with the experimental and numerical results and comparison. So now, these things in hand, what can we do? Now the framework is, we have a decent framework. Can we embed in it the constitutive model of blood? As I mentioned, blood is a very complex material. It shows shear thinning response and viscoelastic response. And in order to model it, either we model each of the constituents, which will be discrete representation, or some homogenization techniques can be applied. And all-right B model is used as a continuum model. All-right B model has a reactive stress to incompressibility and additional stress, which has viscous part and an elastic part. All-right B model, since this is an incompressible fluid, then both elastic and viscous terms should be isochoric. But all-right B model doesn't impose that constraint. And that constraint is imposed in what's called the generalized all-right B model, presented by Rajgopal Srinivas in 2000. And then we worked with Professor Rajgopal in a later paper, where this all-right B model was generalized. This original all-right B model, at very low shear rate, has abrupt change in mechanical properties. Abrupt change in mechanical properties give rise to internal oscillation of the internal variables, becomes problematic. So in this paper, we smooth out the model, numerical model, and generally it will have reactive stress, stress S. Evolution equation for S is given here, relaxation time, retardation time, and it has the viscous part, elastic part, incompressibility, or the det B equal to 1 embedded in here. Now, generalized all-right B model needs to now be coupled with momentum balance equation and continuity equation. So when you embed it in momentum balance equation, this is the new term that appears. This differential equation gives rise to one more equation of the constitutive equation. This is the new equation, and the constraint on the constitutive equation. These are 2 equations. We had discussed these equations in last slides. So I'm going to focus on these additional terms that have appeared, plus their boundary conditions. So these are the 2 additional terms that have appeared. B, which is the kinematic tensor, and constraint on determinant of B. We can, along the same lines as we discussed, we can split the velocity field into coarse and fine, and now this tensorial field into coarse and fine. And what will happen? Velocity field in coarse and fine will give us a reduced turbulence type model, because in turbulence we have the 2 terms. When we said the velocity is averaged over time, we don't get all the other terms, but we get a reduced term, a stabilized method. And the split of B into B bar and P prime, look at B prime as a term that will correct the error in the B field. B field should be such that determinant of B should be equal to 1. And if that constraint is violated, then this fine B term comes in and corrects that. So this is the final mixed form. The terms in the black are Galerkin, fully preserved. Terms in the blue, I showed you previously from the momentum balance equation. These red terms are the new terms that have appeared because of this term in here. Let's take a look at some results. This is the given velocity field. For, again, it's a problem for which, let's say, mathematical fields are available. We can look at the convergence properties of the method. So velocity field, and this is the magnitude of the B field, and now we can compare our results with these exact solutions corresponding to these configurations. This is L2 norm of the B field, and we have 8-node bricks, 27-node bricks, so P refinement, 4-node tetrahedra and 10-node tetrahedra, P refinement. T4 and B8 are linear elements. Linear elements, L2 norm should be 2. And here we are getting a rate of convergence of 2. This line is rate of convergence 2. And for 27-noded bricks or 10-noded tetrahedra, these are quadratic elements, rate of convergence should be 3. This is asymptotic 3. Likewise, the constraint on the determinant of the stretch tensor has a rate of convergence of 2 for linear elements and 3 for quadratic elements. So it means that mathematically, the method is variationally consistent, is providing us the correct rates. I'll now show you some engineering problems. This is the channel flow, viscoelastic flow going over this channel. And we're looking at this cross-section. This is a true thickness cross-section value of sigma xx for various Weisenberg numbers and comparison with different Weisenberg numbers, some other methods that people have proposed in the literature. Here is along the symmetry line, along the surface of the cylinder and in the symmetry line. These are the stress. This is over the cylinder and in the wake of the cylinder, and again for different Weisenberg numbers. What I want your attention, I want to draw your attention to is, look at this determinant of the generalized Aldrich model. It should be equal to 1. This is color-coded. This is exactly preserving that property all the way through. And I'm also showing you Aldrich model, and if we take the determinant of that, the determinant is 102. This is where these models numerically fail. And so imposing that constraint is a very, very important constraint. It's an internal constraint, but needs to be satisfied. With this in hand, we can now look at some interesting engineering problems. This is blood flow through an artery. This is actually a patient-specific case where there is stenosis and this aneurysm. This is a carotid artery. We are using here a reduced shear model. And what I want your attention, draw your attention to is that as the flow goes to the end of diastole, there is a lot of this red buildup. This red buildup is viscosity buildup. And when the pulse comes in again with the heartbeat, this high velocity impulse comes in, shakes the blood, desegregates all the blood cells, and life is better. Viscosity decreases. But when we are not able to do that, when we don't do that, or there is a weight, so, and this is 20% of the heartbeat cycle, so 80% of the heartbeat cycle, actually blood has a tendency to coagulate, so its viscosity is building up. And we use this model in some of, so here are the snapshots. This is at this particular point. A is at this point at the end when the velocity is low, and you see substantial viscosity buildup. And when the pulse comes in, this blue region is, so it means it comes in, it breaks it, reduces the viscosity, pushes it forward. And we have used this in one of our applications where we were looking at ventricle assist devices. There are multiple ventricle assist devices. There are some in which the pulse is steady, and they give rise to a standing wave. And that standing wave makes pockets where blood can stay long enough so that it can develop viscosity, and then it's pushed forward. These kinds of ideas can be used to add modulation, frequency of pulse, and magnitude of pulse so that you can just break it. So you can optimize these kinds of things. So we can apply this to bigger systems. This is blood flow in patient-specific aorta, femoral. So again, this is a patient-specific situation. But in my opinion, biofluid dynamics it has a lot to offer to look at viscosity. But the beauty of biofluid dynamics comes in when you bring the tissue in it. That is where tissue grows, it adapts, it responds to mechanical and chemical stimuli. That is where biomechanics is heading. So I'll take you, in the last few minutes, I'm going to take you to this particular model of growth or cross-linking in tissue mechanics. And as I said, tissue is not just a mechanical material. It will respond to stimulus. How can we bring that thing into picture? So it will grow, it will develop anisotropy. So let's take a look at this smooth muscle. So it has fibers, it has cells, and in between fibers and cells is nutrients. Mass can change between nutrients, and cells can grow, fibers can grow, and at some point we have to use some kind of homogenization idea. If we discretely model each cell, it will be a very computationally intensive process. If we can use some, so yes, we can use some homogenization, but homogenization should be such that the characteristic of growth of the constituents is not compromised, which means that if these materials should be able to grow independently, should be able to move around independently. And their movement, independent movement, then needs to be accounted for, and that is accounted for by interactive forces between these constituents. So here is the whole framework. So we have this reference for the scaffold or the fibers, reference for the matrix, which is the cells. The cell and the nutrients can exchange mass, cell can grow, or cell can die. It can happen either way. So this is the reference. And so when we are doing numerical calculations with these mixture theories, which are not constrained mixture theories, and we are in this current configuration, we have to find out what were the two particles which are right now at this particular point and interacting, where were they coming from? And so for that, we need some kind of a projection techniques, and those techniques are readily available in the literature of plasticity, closest point projection algorithms. So we can borrow some of those ideas from and apply it in this particular case. So each constituent has its own momentum balance equation, and there is an interactive force, which is the relative kinematic force between. There is a relative force between the nutrients that are flowing through the fiber in this matrix system. That is the drag force. These are the interactive forces that need to be. So we have momentum balance equation, mass balance equation, and constitutive model. The constitutive model are based on the notion of hyperelasticity. And in here, we are using this orthotropic for scaffold and the homogeneous isotropic for the case of matrix. And these are the functional forms that are in Cohen and Steinman, and we are using those for our numerical calculation. So I'll show you this framework. So this framework accommodates the total kinematic deformation into a growth part and an elastic part. And each particle, each point can grow by changing nutrients, changing mass with the nutrients independently. So it is an incompatible state. It becomes compatible when we superpose on it elastic deformation. So each of the constituents, both the matrix and the fibers, follow this kinematic framework. And each of them satisfy this weak form. This weak form has incompressibility, incompressible material. Incompressibility we addressed in the case of fluid mechanics. Issues is exactly same in this particular case. We can develop a multiscale formulation and address incompressibility for this mixture theory, and that is what we have done. But would I gain a lot by redefining it? No, it's exactly along similar lines that we did before. So that is the framework. Mass grows, the cells grow by exchanging mass with the nutrient. This is a ODE. We impose that at the integration point between the nutrients and the matrix. So in this framework, what we have implemented, the matrix, the cells grow, the fibers are not changing mass with the matrix or with the nutrients. This is a simpler model that we have, but still it becomes very involved. So this is the framework. And as I mentioned, that the interaction between the constituents is taking place through the interactive force field as well as with mass conversion. So question is, in this framework is, from a numerical point of view, how do we find the interactive force field? Because it is an unconstrained thermodynamic system. Mass constituents stay inside the thermodynamics, but the relative motion of the constituents has been relaxed, and that should be relaxed because that is how material grows. So this is the kinematics of that. You have material configuration for the scaffold or the fibers. You have material configuration for the matrix. And this mapping, so all of this is sitting in here. All of this is sitting at this particular point. So what it says is that while we are doing calculations to calculate the interactive force field, we need to go through this framework to be able to find where this particle came from, and likewise in the other case. And once we do that, we have a mathematically consistent framework to embed this whole framework in. So our contribution in this was the computational method where there is freedom of motion. We are not enforcing a constraint mixture theory, and free anisotropic evolution as matrix evolves, anisotropy of the system evolves with it. I'll show you one last numerical example. This is scaffold, matrix. These are the functional forms that we have used here. So we are uploading the system in this direction. So as we load it, and then we hold it there. And we let time pass, and material gains strength. It's a stress-driven density growth. And so as the matrix becomes stronger and stronger and can take more load on long time, the fibers become this, they get unloaded. This is the transfer stress. In the transverse direction, as we pull, The fibers are strong, so they maintain. The matrix is soft, pulls in. So the forces in the lateral direction is that the matrix is being pulled in tension, the fiber is in compression, and as time passes, as the matrix becomes strong, it carries more load, fibers have to carry additional load. So this is a representative of the long-time behavior of this particular material. I will now embed it in this aortic aneurysm. As I mentioned to you, most interesting phenomena are taking place, and here we are looking at aortic aneurysm. Aortic aneurysm is again considered to be a major issue. Its long-term stability becomes an issue. Not every aortic aneurysm is dangerous in the sense that it will disrupt or it will break or rupture, but some are. But what I want to draw your attention is this is 5 cycles. In first 4 cycles, we are doing rapid evolution of the mechanical properties of the tissue. And the last 2 cycles are representing the 2 heartbeats. So we can use this kind of models to rapidly look at the long-term behavior of an aneurysm. And so if you look at it, in the beginning, the viscous development, so viscous red portion is less, but as this geometry changes, because of this pouch in here and recirculation, there is a pocket where blood can stay a little longer and has the propensity to coagulate. So this kind of analysis can tell us risk involved in terms of a stroke. What we have done in here is, since we did full calculations, we know what the velocity and pressure field is here, velocity pressure field in here. We can design, or we can derive the resistance boundary conditions and apply here. So even though we are using a more expensive computational model, but we are using it locally while having full information of the system. In here, what we have from a mathematical method development point of view is a monolithic coupling of a highly viscoelastic solid to a highly viscoelastic fluid, nonlinear couple. This is different from typical flows where flow is coming uniformly. It is stop and go. This problem is much harder to analyze. Here is the close-up view. Now we are looking at cross-section at the last 2 cycles, what happens in a typical heartbeat. Again, as in systole, as the pulse comes in, you see that it breaks the red coagulation, and then this coagulation starts picking up again the interaction. We can also look at not only the detailed features, and this is between a healthy and a diseased case for all other mechanical properties being the same. If you look at the flow features, there's a lot of recirculation. There's a lot of wall shear stress, which we can pull out in here. So not only the mechanics of flow, but also the issue of tissue evolution, the stresses on tissue, wall shear stress is again considered to be a reason for the growth for the disease to evolve. So as my concluding remarks, I've presented a framework for developing residual-based closure models for large eddy simulation. I showed you 2 different models. With respect to the refined model, when we look at the earlier model, that is a reduced order turbulence model. And that is why stabilized methods have been able to give good results. A direct treatment of fine scales via bubble functions, it lets us derive analytical expressions for the closure models that can be very quickly computed. There are no filter functions. There is no artificial viscosity in any of these calculations that I showed you. As I mentioned, you can think of it as DNS because model is derived off of the Navier-Stokes equations. We have embedded viscoelastic shear rate model in this framework. I've shown you a tissue model for density growth. I didn't have enough time, of course. I had to. I quickly went over this particular model, but I'll be happy to answer any questions related to that. And from a numerical perspective, it's the monolithic coupling that stabilized fluids and stabilized solids give you so that you can take on problems which have a lot of numerical beating. Lastly, I'd like to acknowledge my graduate students, my collaborators, financial support from different agencies. Thank you very much. Yes, of course.
Yes.
Thank you so much.
Thank you.
Can you introduce yourself?
Yes, so I'm Grace. I'm currently a graduate student. So my question is on your global and local air. Can't remember the slide, but roughly, approximately, how much local and global air are you seeing in your models?
Okay.
And is is it adding it into your variational equation, how much more expensive is your computational, how much larger is your computational cost if you add it back into your equation?
Okay. Let me see if I can quickly roll it back. It's a very interesting, it's right here. It's this particular one. So if you take a look at this distribution, what happened to, yeah, showed up. So if you look at this numerical numbers in here, it is 10 to the power -4, -5. So so 0.00, so it's fairly well resolved. Okay? So global error, yes, global error is the error which is the pollution error that is in the, it is roughly, this is blue, and what we see is green. Green is 0.04, so 4% error in here. Okay? This one is 10 to the power -7, and this is orange, so 0.0001, fairly well resolved. Okay? And so first of all, the cost of computation of the local error is exactly same if you are doing solid mechanics and you calculate the displacement field, and then you say, I want to calculate the stress field. You go at the element, and you look at the displacement field. You construct your strain field and multiply by constitutive model, right? Parameters. You can get it for every element. This is exactly a loop that you can do over each element to calculate this one. It's very fast. And the global error, since global error is coming off of the last factorized matrix, you don't have to make them matrix or factorize it. Just don't throw the matrix away. If you are going to do an analysis of your solution at the end of the step, then in your code, don't throw the code away, the stiffness matrix away, the factorized stiffness matrix, or don't overwrite it. Just keep it there. So it means all you have to do it, once you calculate this, one solve over all the elements, then plug it and make the right-hand side vector and one back substitution. That's it. It's a very cost-effective way.
The sentence that you used that went very fast, this was with the non-Newtonian fluids, Arif. You said something about oscillations with the B tensor.
You're right.
So I don't know what happens here precisely, but as you know, in plasticity, if you have a back stress and you use these various rates, if you do a simple shear problem, you get these oscillations.
Right.
Do you get them here too?
Those oscillations, in this particular case, because we were using the fine scale feature, we were,
Can you show that equation?
yeah.
Kind of fast.
Yeah.
You had some convected rate of
Yeah,
your
it is the upper convective rate, and let me here. That's the one.
Yeah.
Yeah.
So that equation which is not in red, that one oftentimes is problematic because of the upper convective.
Exactly. So this is the lambda b, which is imposing the constraint on b. And on the very next slide, on this slide, that is what I tried to show. It is uniformly converging. So through this mechanism, we were, yeah.
The physical value of the resulting elastic stresses that you compute from it.
Yeah.
Are they, if you do a simple shear problem,
Yeah.
are the stresses monotonically increasing or stable, or are they oscillating?
They would oscillate.
Then there's a problem.
Yeah, they would oscillate.
Physically, you don't see that.
Yeah. So in this framework, I think, as we discussed, that the rates are all, they're subject to question. And the framework, which is a better framework, and we discussed that, is multiplicative split. It gives you a much robust, it's a much more robust framework. Here, issue was to implement a method in which we can look at the evolution and constraint on B coming from Aldroyd B model, which is not enforced there, and how we can enforce this.
In a lot of physical problems, the variation of scale is quite continuous.
Yeah.
Now, how do you, in numerical analysis, how do you decide where the borderlines are? How do you choose what is large scale, what is small scale, what is intermediate scale?
So in this particular case, given your mesh, so mathematically we say coarse scales belong to the sub-range of computable scales, or they are a subset of the computable scales. So given a mesh, the mesh will pick certain features that it can resolve, and everything else will be cut off, and the fine-scale modeling will bring that thing in. So if you change your mesh, that cutoff line will move back and forth. If you have a very coarse mesh, then you are putting a lot of burden on your fine-scale model to be able to compensate for the lack of consistency, lack of physics in the coarse scales. And if you have a fine mesh, then that problem is easy to. So we don't have to go in explicitly put a cutoff there. Whatever is not resolved will automatically go in the fine scale range.
Suppose you use different kinds of, different choices, 5 different choices. Would you be sure that you always get the same result?
5 different choices. And
5 different choices of separation of scales.
Yes. So some of the results that I was showing for turbulence, I said we have coarse mesh and fine mesh. That was exactly done for this thing to compare with the response of coarse mesh and fine mesh with, let's say, experimental data. And so that was exactly to show that when the mesh is coarse, your fine scale problem is doing a lot of work for you, but it's reproducing the same physics.
In that fiber matrix problem,
Right.
Is the creeping accounted for of the fibers?
Not yet. We have not accounted for, but that would be
the important factor.
absolutely.
for prediction?
Tissue adapts itself.
Yeah.
So if it were an engineered material, then yes, you would have to bring the creep model as a part of it. If it is a material that grows, then we have not done experiments, numerical experiments on that, but you can think of creep as an evolution process that is taking place in that tissue which is live, and how does its properties increase or decrease. So in the model, you can embed that feature in to account for it. But it will become a part of your growth part, that the tissue is growing, and that growth is creep effect. Its properties are growing, evolving, and you can absorb it in there.
Okay, well, if no other questions, we would like to thank you again for this exciting talk.
Thank you.